Dear students, in the previous class, we have discussed the sampling distribution of the sample mean, where the sample mean is the random variable. And as I told you in the last class, this sampling distribution is used to make inferences about population mean. That is, sampling distribution is used to make inferences about population parameter mu. But a problem is, generally, we do not know the shape of the sampling distribution. Generally, we do not know the shape of the sampling distribution, as population is unknown. And without knowing the sampling distribution of the sample mean or the sampling distribution of any estimator, we cannot make inferences about the population parameters. Anyway, in the context of arithmetic mean, there is a result. The result is that we can approximate the sampling distribution of the sample mean by a normal distribution. That is, under certain conditions, the variable x bar is approximately normally distributed. Under certain conditions, the variable x bar is normally distributed. Remember this, we must know the sampling distribution to make inferences about parameters. And the shape of the sampling distribution will be known if and only if the population is known. But in most cases, the distribution of the population is unknown. But we can approximate the sampling distribution by a normal distribution under certain conditions. Conditions we will see later. That is, the variable is x bar is approximately normally distributed. The variable, the random variable x bar is approximately normally distributed. Now remember this, a variable is said to be normally distributed if the shape of the distribution is, if the shape of the distribution has the shape of a normal curve. Remember this, a variable is normally distributed if the shape of its normal curve has the shape of a normal distribution, that is bell-shaped, symmetric around mean, something which we have studied, with the parameters mu and sigma square. So x bar is normally distributed means the shape of the distribution of x bar has the shape of a normal curve with the parameters mu and sigma square. So to approximate the sampling distribution of the sample mean by a normal distribution, to approximate the sampling distribution of the sample mean by a normal distribution, we must find out the mean and variance of the random variable x bar, mean and variance of the random variable x bar. And we denote the mean and variance of x bar as mu of x bar and sigma square of x bar. Mean of x bar and sigma square of x bar. We approximate the distribution of x bar as a normal distribution. So for this approximation, we require the parameters of the distribution, and we denote the parameters as mu of x bar and sigma square of x bar. And remember this, we are dealing with the random variable x bar. So first we consider mean of x bar, mu x bar, mean of x bar. Now there is a simple relationship between the mean of the variable x bar and the mean of the variable under consideration. The relation is mu of x bar is equal to mu. That is, the mean of the sample mean is equal to the mean of the variable under consideration. Mu of x bar is equal to mu of, say, x, if the variable under consideration is x. And this is a property of the estimator x bar that we will see later. And remember this relation holds irrespective of the sample size. Whatever is the sample size, mean of the sample mean is equal to mean of the population under consideration. Whatever is the sample size, mean of the sample mean, that is, the mean of all sample means is equal to population mean. And in this example, we have mu as equal to 80. If you take samples of size 2, we have derived 10 x bar. If you add together these 10 x bar, for n is equal to 2, then mu of x bar is equal to 80. If you are using samples of size 4, you have generated how many? 5 sample means. Again, if n is equal to 4, mu of x bar is equal to 80. That is, the sample mean is always equal to population mean. Sorry, the mean of the sample mean is always equal to the mean of the population under consideration. This result holds irrespective of the sample size. Now let us see what is the variance and hence the standard deviation of x bar. Standard deviation of x bar. Now, the population standard deviation sigma is given as root of sigma x minus mu square by n. Sigma x minus mu square by n, and it will give us, if you do the calculations, root of 11.6 is equal to 3.41 inches. 3.41 inches. That is the standard deviation of the population. Mean 80, sigma 3.41. And for the samples of size 2, sigma x bar is, for samples of size 2, sigma x bar is, if you do the calculations, we have mu, that is, for samples of size 2 or for whatever it is, mu of x bar is 80. And we have generated, for samples of size 2, we have generated 10 samples. 10 sample means. So, if you use the formula, sigma of x bar, you will get sigma of x bar as root of 4 by, that is, actually it is root of sigma x minus x bar square by n. N here is 10 because we have generated 10 observations, and this will give you what is known as root of 4.35, and this value is equal to 2.0. If n is equal to 2. Now let me generalize. If n is equal to 1, then sigma of x bar is equal to 3.41. N is equal to 2, sigma of x bar is equal to 2.09. N is equal to 4, sigma of x bar is equal to 0.85. N is equal to 5, sigma of x bar is equal to 0, like this. So, as the sample size increases, standard deviation of x bar decreases. You can do the calculations if you want. The only thing we require is this property. As the sample size increases, the standard deviation of x bar decreases. And this we did by using a numerical example. Now let us generalize it. That is, the question is whether there is a formula that relates the standard deviation of x bar to the sample size and the standard deviation of the population. Whether there is a formula which relates sigma x bar to sigma x and n. The answer is yes, there is a formula which relates the standard deviation of x bar to the population, the standard deviation of the population and the sample size. When sampling is done without replacement from a finite population, sigma of x bar is root of n minus n by n minus 1 by sigma by root n. And this part is known as a correction factor for small samples. When sampling is done with the replacements from a finite population, sigma of x bar is sigma of x bar is sigma by root n. And this is the formula which we will use. When sampling is done without a replacement from a finite population, this is a correction factor for using a finite population. When with the replacement from a finite population, sigma x bar is equal to sigma by root n. And this is the formula which we will use in inferential statistics. So the point is, if the population is distributed with the mean mu and variance sigma square, then the sample mean is distributed with the mean mu and variance sigma by variance sigma square by n, or standard deviation sigma by root n. So in the form of a definition, for a sample of size n, the standard deviation of the variable x bar equals standard deviation of the variable under consideration divided by square root of the sample size. Standard deviation of x bar is equal to standard deviation of the variable under consideration divided by the square root of the sample size. That is sigma x bar is equal to sigma by root n. Sigma by root n. So, if x is the variable with mu and sigma, x bar with the same mu and standard deviation sigma by root n. This is a relation between x and x bar. Now, we have already defined what is the sampling error. Now, there is a relation between sample size and sampling error. The relation is the larger the sample size, the smaller is the standard deviation of x bar. And the smaller the standard deviation of x bar, more closely the values of x bar cluster around mu. So, and the mean of x bar is equal to mu. So, as the sample size increases, you can see the standard deviation of x bar decreases because as n increases, this denominator increases. So, x bar cluster around mu. The exact distribution will be discussed in the next class. Now, because standard deviation of x bar determines the amount of sampling error, standard deviation of x bar determines the amount of sampling error to be expected when a population mean is estimated by sample mean. It is known as the standard error of sample mean. Standard error of sample mean. Standard deviation of x bar is known as the standard error of sample mean. It is known as the standard error because it is the amount of sampling error expected when a sample mean is used to estimate a population. And in general, the standard deviation of a statistics is known as the standard error. That is, standard deviation of the statistics is known as the standard error of the estimate. And remember this, if x is a variable, its mean is mu and its standard deviation is sigma. If x bar is the variable, the estimator, its mean is mu and its standard deviation is known as the standard error. So, standard error is nothing but the standard deviation of the estimator, whether it is x bar or whether it is sample standard deviation, sample correlation coefficient, whatever it is. So, we have defined what is a sampling distribution. We have also defined the mean and the variance of the sample mean x bar. And the standard deviation of x bar is known as the standard error because standard deviation of x bar determines the amount of sampling error that we should expect when a population is estimated, mean is estimated by a sample mean. So, it is known as the standard error of sample mean. And in general, the standard deviation of any estimator is known as the standard deviation of any estimator is known as the standard error. And the sampling distribution of the sample mean will be discussed in the next session.